Okay, hi everyone. Wow, this week it's intense, moderating a whole week, and it just keeps on coming. It feels like it's Saturday for me now. Here's the, and that's a good thing actually. I could go for more of this week. I just want to go over some announcements before we get to our second keynote talk this week from Filippo Fraternali. We know this slide and this slide. I think we all know the Slack channel now. A couple things about this week's ongoing conversations. We had two yesterday, the Milky Way and the CGM, and those were both well attended, about 25, between 15 and 25 for each one. There's two more today. We have Halo 21 ISM CGM, a featured conversation with Shmuel and Miao. That's at 12:30, and there is actually another one, which is sort of an ongoing conversation with, and Joe Bircha told me about this, at 11:30, and those don't overlap, and you can go look at the Zoom links in the Slack channels. Yeah, I think that is pretty much it. I don't know if anybody else, any of the other organizers have any announcements. Great. I will have the pleasure of introducing Filippo Fraternali, who will give a featured or a keynote talk today. And we have a very, he was very popular, so we have 5 people on the panel. Discussion starting at 9 a.m. Pacific time. Jakob Fairman, Miao Li, Nir Mandelkar, Frank Vandenbosch, and Jess Work. So without further ado, I am going to turn it over to Filippo.
Thank very much you and the other organizers for putting together this and for inviting me. You are doing really a splendid job. I was telling Jessica, I'm really impressed. There is lots of enthusiasm, lots of great talks and discussions. Congratulations. And it's a great pleasure to be here and give this second talk with this very difficult title. Let me see if I can get my laser that probably you should see now. Should try to answer the question, what does the Milky Way tell us about the CGM? So my talk has the following outline. I will start with things that we have learned about the Milky Way and we may have forgotten. Then I would go to why do we want to complicate our lives? And I'll finish with embrace condensation and be happy, obviously. So things that we have learned about the Milky Way and we may have forgotten, or this is already long, but there is another title, learning about the CGM from below. So really from the disk where we are. Thing number one, the first one is that the Milky Way's disk had a quiet and relaxing life. This is clearly shown by a number of evidence. The first one that I'll mention is the fact that the star formation history is known since a very long time, has remained relatively flat. It could have been a bit higher in the past, but not much. These are 2 examples of star formation histories in the solar neighborhood, and to some extent the solar neighborhood is a small place, but up to a certain point, because due to stellar migration, the solar neighborhood actually, in the solar neighborhood actually you see stars that are coming from different parts of the Milky Way. So it's not such a small portion of the disk. But then now there are new determinations where we actually see much more of the disk. So like, for example, this apogee data that go at much further distances. And the star formation rate is found to decline a little bit, but we are talking about a factor 2 potentially from redshift to today. The other thing, the other evidence that I like to mention is dynamical. There is this wonderful, if you look at the disk of the Milky Way, there is this wonderful relation between the dispersion, the stellar velocity dispersion and the age of the stars. And this is actually extremely well reproduced by very simple models. These are actually, there is a series of papers by Omer Albini that they're very very interesting papers. If you don't know, I recommend them. They have a disk evolving essentially in isolation. There is star formation, etc. The disk develops a bar, etc. And they look at several properties. And many of these properties match very well with the disk of the Milky Way. These are different models. The red doesn't match, but all the others match some different parameters. So you see that the dispersion up to at least 7 gigayears ago are very much in line with simply, these are stars that are simply warmed up by the interaction with spiral arms and molecular clouds and something like this. So the disk lightly puffs up a bit, especially at older time. So just to say, no major drastic event. And this, to some extent, is also given that Gaia has been mentioned, and you cannot these days really give a talk about the Milky Way without mentioning Gaia results. But to some extent, Gaia results are very much confirming this, because now there is this evidence of at least a certain consensus of the event of a merger that, well, it's not quite major because we are talking about this mass ratios that is called, depending who you're talking to, Gaia Enceladus or Gaia sausage. And this thing should have interacted and merged with the Milky Way between 10 and 11 gigayears ago, 8 and 11 gigayears ago, and the mass is this. And the idea is that this merger has an important effect in the formation of the thick disk, maybe has puffed up the disk that was there, formation of metal-rich halo, etc. There are possibly other mergers. Stellar streams several stellar streams are found, but they are mostly they seem to be more or less in the same period and at smaller masses with respect to this one. After Redshift 1, not much happened in the Milky Way. There was Sagittarius dwarf and Magellanic clouds coming in, and these have all remained in the halo. And it's important to remember that the stellar halo is still only 1% of the stellar mass of the Milky Way, which is very minor. I'm not considering the Magellanic clouds in this count. So really diffuse stars, globular clusters, Sagittarius as well. So this really says that most of all stars in the disk simply formed there, stayed there in the mold. So that was the first point. My second point really goes back to chemical evolution models, and is the following. Gas accretion has occurred continuously in the Milky Way and a relatively low metallicity. So this is, again, something that really goes back very much in time. I apologize if you know all these things, but I thought it was important to point them out and also make reference to the new findings. So this is, as I said, known from many chemical evolution models. These days, this is a figure that comes actually from my book that after 5 years of pain finally came out last year. But the model is a model from Schoenrich and Macmillan, and it's a chemical dynamical model of the Milky Way. And you see that this model reproduces very well the metallicity distribution of stars, in the solar neighborhood. But and if you consider instead the famous closed box model where there is no accretion, this metallicity distribution is completely not reproduced. This is another way to look at the so-called G-dwarf problem. And then the other thing that, by the way, the metallicity that these models require for the accretion is not 0. It can be a few solar, 0.3, 0.4 solar, the models will work. It doesn't have to be solar. The other thing that you can derive with these models is accretion rate, and you find that the accretion rate somehow, depending on the star formation rate that you are considering, follows the star formation rate below, because of course there is gas return from stellar evolution that tends to compensate for the accretion. And if you have outflows, then you need more accretion, of course. Then accretion. This is a bit more controversial. So not really in the Milky Way, but in general. So gas accretion in the Milky Way occurs essentially vertically over the disk, not at the edge. And this, I'm realizing that in the CGM community is not really the picture, as this masterpiece from Jessica demonstrates. So the idea is that accretion occurs at the edge of the disk, and then has to move to the center. So this, for me, I've said it other times, is problematic because you need very high velocities in the disks of order of 10 or more kilometers per second, and these in local galaxies at least are not observed. But what I want to say today is mostly the Milky Way perspective. And from the Milky Way point of view, essentially, most chemical evolution models actually do not even include radial flows at all. They have the gas coming down vertically and stays there. So just to say, this is probably wrong, but there is really no need for this kind of flows. Then a model that finally included these radial flows is the model by Schoenrich and Bin in 2009. And this model, just to make the point, it reproduces really many observables and observations of the Milky Way of different kind. Here, this is a chemodynamical model, so it reproduces the velocity of stars and the metallicity at the same time. So it's a very sophisticated model to some extent. And in this model, they have tried to see how much accretion is vertical and how much accretion is radial, and they are essentially finding that most of the accretion is vertical. They have a model with 30% of radial accretion, but that is excluded by the data. So most of the accretion in the models of the Milky Way, and I'm not talking today, I'm talking throughout the history of the disk. So it's vertical. And with vertical accretion doesn't necessarily mean that the material that comes down rotates as fast as the disk. This would be strange, to be honest, and probably unexpected. So what we can imagine in this simple picture here is that the material that comes down has locally an angular momentum that can be in principle as angular momentum, some angular momentum, but it can be in principle a bit different from the disk. And in particular, if the angular momentum of the accreting material is lower than here I'm talking specific angular momentum, than the disk, then you develop radial flows. So radial flows are probably there. There is no doubt about that. But the interesting thing, and this is a result that we have obtained a few years ago, is that these radial flows actually influence the metallicity gradient, and you can use the metallicity gradient, in this case in the Milky Way, to try to understand the angular momentum, to infer the angular momentum of the accreting gas. And what we did in this paper with Gabriele Pezzulli, we considered a model, a chemical evolution model, in which there is this parameter, which is the angular momentum mismatch. Okay, so if the accreting material has the same velocity as the disk, this angular momentum mismatch is 0. So the material comes down, no radial flows. If there is a deficit, then you have radial flows. And if you evolve the model, I'm not going into details, but essentially for different alpha, we have different gradients, different metallicity gradients. This is the prediction of the model. And this is the range in metallicity gradient that is allowed by the Milky Way. And so you can say that alpha has to have a value of about 0.2, 0.3. I'm saying 0.2 because we have also other type of models. So that the range is 0.2, 0.3, which is very interesting because it tells us several things. It tells us that the accreting material has to have angular momentum. Okay, it's not 0, but this we knew it to some extent. But the rotation of the accreting material locally should be 70, 80% lower, so rotate more slowly than the disk in that position. And a model like this produces very mild radial flows in the disk of 1 kilometer per second. That they are almost impossible to detect anyway. Okay, so my conclusions for this first part are the following. Let me summarize what I have said. What is the Milky Way telling us about the CGM? It's telling us that the CGM has gradually accreted onto the disk over the last, certainly over the last 8, 10 gigayears. The accretion seems to occur over the disk, not at the edge, at least most of it. The accreting gas is metal poor, metallicity of 0.34 solar or less. The accreting gas has angular momentum, but locally rotates a bit more slowly than the disk. Okay, this is from looking at the disk. Now I'm moving to the second part, which is why do we want to complicate our lives? And this is divided in 2 parts. The first part is the following. This is a message for Jessica. The Milky Way is a wonderful spiral galaxy. We have to realize this. In the Milky Way, and also the point is that in the Milky Way we can study 1.8 billion stars these days with Gaia. The details of the ISM, the structure of the CGM clouds, the halo population, every single line of sight we look around, there is the Milky Way. Okay, so it's really a pity not to use it to understand galaxy evolution in general. And anyway, if you think about it, in the basic things, the Milky Way has spiral arms, none of this flocculent nonsense of other galaxies. The Milky Way has a bar, which is, I mean, common in spiral galaxies. The masses of stars, masses of dark matter, of gas are more or less okay. Let's look at this plot here. It comes from a paper that we published last year. This is the stellar to halo mass relation, M star here and M hero in the x-axis for several spiral galaxies obtained by fitting the rotation curve, so that the halo mass is really measured in this case. And you see that the Milky Way is this cross here that sits very nicely in the middle of other spiral galaxies. Okay, you can argue that the Milky Way may have a little bit low star formation rate with respect. This is a paper where they have put the Milky Way. If you can see it, it's difficult. It's here in the main sequence. This is the main sequence, but I have revised the position, and this should be the yellow dot. So I would say that if we were to send an application to a universal institution that has to grant the Milky Way the status of normal spiral galaxies, this application will be approved. So this was the first. The second one that is maybe more relevant for what we are discussing here is what do we do with this list of pieces of evidence that I've discussed before? So let me remind again. The CGM has gradually accreted over the disk, low metallicity. The accretion occurs at lower angular momentum locally with respect to the disk. My question to you is, does something come to your mind? Something comes to Crystal Math's mind. So to me, when I hear all this comes to my mind. So the hot gas, the hot halo surrounded the Milky Way. And now I go through these points and I tell you why. First of all, accreted over the last 8, 10 gigayears. As far as we know, the hot halo, the corona of the Milky Way, could have been there since Redshift 1. This is the famous Deckel and Beerbohm distinction between hot mode accretion and cold mode accretion. And you see that the Milky Way is crossing the line essentially at Redshift 1 or a bit before. So from the theoretical point of view, we can expect that. An interesting point that goes back to Mary Passman's talk of 2 days ago is that she claims that we see the Milky Way with interaction with dwarf galaxies, and I believe that this is true. But several of these dwarf galaxies have lost their gas long time ago, very long time ago, and so the corona must have been there also 7, 8 gigayears ago. If we want to claim this. We know this very well because we know the star formation histories of these dwarfs. So this is, for me, is a check, although it's not completely green, if you notice, it is yellow. The second, the accretion occurs over the disk, not at the edge. This is completely a green check because the corona is in contact with the disk. The accreting gas is metal poor. Here, there are the determination in the Milky Way that mostly by Bregman and his group are of, I mean, around a bit larger than 0.3. Also, there is 0.4, 0.5. These are a bit at odds with the determination in external galaxies. We are never talking about solar, so I would say that this is also pretty much a check. And the last thing is also very interesting because this need for relatively low angular momentum locally actually fits very well with the very difficult estimate that has been tried in this paper here of the rotation of the corona, around 75% of the rotation of the disk. This matches with what I said before, the metallicity gradients, and also interesting matches with prediction from cosmologically motivated angular momentum distributions. So what do we have to do? Obviously, the corona has to cool to allow this to happen. And the cooling can occur in different places, but the first place that comes to mind, because the maximum of the density you would think is in the center of the corona, which means also the center of the disk, you would expect most of the cooling to occur at very small radii. And this is bad, because that gas has low angular momentum, and the disk doesn't grow inside out, and Ben knows very well that you need lots of feedback to essentially eject all this gas that you didn't want it in the first place. Now, what the solutions could be? One solution that I think is very interesting is the presence of the Fermi bubbles. That maybe they are there for a reason, because the black hole is reacting to this attempt of accretion, and this is certainly something that would be good to keep the inner corona hot for longer times. Still, the gas has to cool further out. Okay, and to cool further out, there are several possibilities. One is the precipitation model, instabilities that Mark Voigt had pushed and presented in several papers. Another possibility is the rotation of the corona actually triggers instabilities, also because the rotation tends to can tend, it depends a bit on the distribution, but can bring the higher density further out, not in the center. And the fourth possibility, which is obviously my favorite, is the condensation via the galactic fountain. And so this brings me to the third part, and I'm more or less on time according to my my watch, which is the condensation part. So condensation. With condensation, we mean that when you have interaction between cold gas and hot gas surrounding, this produces essentially the increase of the mass of the cold gas. And this was shown in 2010 by Marinacci et al. And in that paper, they also showed that the condensation can induce the cooling of the corona to trigger the star formation, or to feed the star formation in the Milky Way, and also that to find these things you need a very high resolution for your simulations. In a later paper with Armilotta, Lucia Armilotta, we investigated the possibility that actually thermal conduction can play a role. Here you see a very nice simulation with lots of condensation taking place here in the wake of the cloud. And if you have thermal conduction, you see a very different evolution of the wake, but still there is quite a bit of gas, cold gas here developing because the hot gas is cooling down. And when you plot the mass of cold gas, also in the case of thermal conduction, you have condensation. Okay, so the title here is Drummond, my friend. I've seen, I don't know if you are listening, but I'm sure my words will reach you one day. I've seen your excellent review, excellent talk, and I've seen that you are completely neglecting this and granting Gronke 2018 the discovery of the condensation. But this is okay, it's not a problem. But then you did something worse, because you made Gronke superheroes. And this is serious. This is serious. So I said, I have to do something. So everybody, please meet the superheroes. Wonder, Armilotta, and Super Marinacci. And let's see what these superheroes have done. Super Marinacci in 2011 went to look whether this interaction with the cold gas and hot gas actually can exchange not only the mass, but also the momentum. And what he found is that actually the fountain itself, because of this interaction with the corona, has to speed up the corona. This is, I can discuss this at length, because this in principle is an enormous problem, because this can behave like a blender and the corona would disappear from the center. Actually, this doesn't happen, because when the velocities between the two media come down, the transfer of momentum ceases, because the corona is cooling and is joining the cold phase. So what this means effectively is that there is a mismatch in velocity between the disk and the corona, and this mismatch is around 75 kilometers per second, and again is more or less the number that I was discussing before. Wonder Armilotta instead, in her paper in 2016, looked at condensation with different temperatures. And the different temperatures that I'm showing here are a bit extreme. One is 1,000,000 degrees and one is 8,000,000 degrees. And what she found is that, as we could expect it, that there is much more condensation when the temperature of the hot gas is lower than when the temperature is larger. And this can be shown here. So there is lots of condensation at 1 or 2 or few million degrees, and then you essentially have no condensation when you go to higher temperature. And this is very easy to understand. If you take the cooling function and you start from here, this gas can be mixed with a very small amount of colder gas, and immediately you are very close to the peak, or even in the peak, and then your cooling proceeds very fast. So the mixing is obviously important, the densities are important, but broadly speaking, this is what's happening. And when you go to Milky Way sort of temperatures, you are still okay. The peak is not so far away, but here is enormously far away. And then the mechanism doesn't work anymore. At everything else the same, so same densities, etc. Can this have a role in star formation quenching? Maybe, but this is another topic. Okay, and the very last paper that I've published on this topic is actually from a few weeks ago, from a master student here in Groningen, my postdoc, Esgar Gronno. And this is really a super sophisticated simulation of cloud that is, you see, shred by this wind, and is producing quite a bit of cold gas condensation. Here we have magnetic field, and we have anisotropic thermal conduction. Here you see the evolution with the magnetic field strength. Even in this situation, the magnetic fields, we knew it, tend to lower the condensation, and so does the thermal conduction, but still, this is the result with magnetic field and thermal conduction, so probably treated, and still we have condensation of around 10% after 60 megayear. So the conclusion from this, and a conclusion from other papers, is essentially that condensation is consistently predicted under certain conditions that actually are met in the lower corona of the Milky Way by all high resolution simulations. The high resolution is a very important part. Okay, now that we're embracing the condensation, we can be happy. And how can we be happy? To be happy, in my opinion, we have to understand what we do with this. And I tell you what I think is very important that we do with this, and with this sketch that I've prepared here. So we have a disk, and this disk has a very small thickness. I'm saying now 100 parsecs, can be a few hundred parsecs, but this is essentially, if you take your gas and you make it warm, so H1, warm H1, at 8 kilometers per second, and you calculate the thickness of vertical hydrostatic equilibrium, you essentially explain the disk, okay? Now, in this disk, there is something more. The supernova are going on, go off continuously, and this produces this larger layer of extraplanar gas that can be up to 10 kiloparsec actually from the disk. So locally in the Milky Way, this thing is seen as intermediate velocity clouds, but the intermediate velocity clouds are just a fraction of all the extraplanar gas that we think is there, okay? And further out, there are the high velocity clouds that, in my opinion, are very much part of the picture, the beta stream. But the most important that I want to point out here is that in this layer, there is, this layer is very important because what we said, all this is surrounded by the hot gas. So in this layer, where the fountain is bringing actually 10 solar masses of gas per year, so it's an enormous cycle, is an enormously large mass loading factor. In this layer, there is mixing, 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 mixing. There is lots of mixing. And so this is really important. And I mean, I understand the importance of trying to explain I understand it very much, the importance of trying to explain the cold gas very far away, see if you can do it with the winds, with the accretion, etc. But here there is an enormous amount of mixing between cold material and outer material and external material, and this has potentially very important consequences. So how do we know all this? In external galaxies, we see it. So this is a H1 galaxy. If here there were only a thin disk, this would be the H1 observation. We see lots of stuff above the disk in emission in H1 with very high resolution observations, and the mass is up to 25% of the total mass. So it's quite a bit. In H alpha, we see it even better. So here you really distinguish the disk, very bright, from this material that is outside. In the Milky Way, we have to remove the disk, but this is doable. So this goes back to Young's talk of yesterday. We have done it in this paper mostly to show what comes out. So this is the whole H1 map of the Milky Way, where you have taken essentially everything. Here you see the disk very well. If you take this at this latitude here, this is a longitude velocity plot data. You can this would be a disk model. We can mask a generous disk model, and there is something that sticks out that is definitely cannot absolutely be part of the disk. And when you put all this together, this seems very little. Actually, you get this. So every line of sight has material that is not part of the disk, is part of this extraplanar gas. Obviously, you see some problems in the subtraction of the disk here. Down here, the Magellanic stream has been subtracted. Also, you see some, but there is lots of material. But this, in some sense, is what you see. And to understand how it works, you have to do an extra step. And to do this, we have built this kinematic model. The kinematic model, essentially, you have a disk, and then you have an extraplanar layer with some parameters. You put yourself in the middle, you look around, and then you compare it with the data. And by doing this, we extracted the properties of this medium. The mass is 3 times 10 to the 8 solar masses. It's the gradient. There is a vertical gradient in velocity because it's rotating more slowly, 15 kilometers per second. And then there are 2 interesting parameters that are in flow of H1 in the vertical and in the radial direction. As I was saying before, the intermediate velocity clouds are just a part of this. But what you really want is a dynamical model. And this dynamical model, we built it particle-based, using because we want to reproduce the whole galaxies, using this pseudo-ballistic approach in which there is ballistic motion. As you see here, this is purely ballistic. So you see that the particles are going out and coming back to the disk because of this ejection. But also we can, because we have the simulations, we can include in this model also hydrodynamical effects. And in particular, we include condensation. And if we include condensation, look at the shape of the orbits. The shape of the orbits changes substantially. This tells you that you can see the difference between the blue and the red. And even more from this plot, here you see that without interaction with the corona, all the particles more or less remain at the same speed as the disk. This is the rotation curve of the disk. But if you interact with the corona and the corona is rotating more slowly, then the particles start rotating more slowly. So we can see if we detect in the data this effect. And then out of this model, we have produced, so there is a kinematic imprint of the cooling of the corona that is rotational lag and these radial inflows that you saw in the orbits. Do we see this in the data? To do this, we have to produce this artificial data cube of the various model that is shown here in terms of some, again, longitude velocity plots, but we fitted actually the entire data cube. And this simply shows you that in some location, so this is a model with pure fountain, this is a model with fountain plus condensation, these are the data. And there are locations like, for example, where you see this arrow here, this model works better than this model, and etc., etc. Here there is less gas than in this model works better. And you do this for the whole data cube, I'm stressing this, and you find a very clear minimum for the value of the accretion rate that this model is supposed to produce. And this accretion rate is essentially gas that is not part of the fountain cycle. This is extra gas. So the fountain cycle is putting up and down 8 solar masses per year of gas, lots of it, mass loading factor of 4 if you are taking a star formation rate of 2. But on top of that, 2 solar masses per year are needed to reconcile the kinematics with what we observe in the data. And we can also get an accretion profile from this that is quite interesting, because then you can compare it with chemical evolution models that have completely different type of constraints. So the other few things that I want to say about this model is that this is a relatively old work, but I think it's relevant for what we say here. What we did in this paper in 2013, we said, okay, but if there is this cold gas that is interacting with the hot gas and is cooling the hot gas, if there is a line of sight that goes through this cooling material, we should be able to see it. And at that time there was this, there were these observations that came out, especially the Lenner and Hauk and Lenner et al. 2012. Now there are more data. We should redo this again, but I don't think the picture has changed completely. So these are observations against the AGNs and also stellar sidelines in the halo. And we said that some of this may be the cooling material that is condensing from the corona. So we took our model that reproduces the H1 gas, and we actually did not change it, and predicted simply what that model would predict for the location of the ionized gas. Okay, the dispersion is larger, the ionized gas is different, but the kinematics is exactly the same as the H1 model. We didn't change any parameter. This is incredible, because you see that most of the observations are actually very much in agreement to predict. The contours would tell you, if you could see the ionized gas in emission, this is what you should see. So that is the idea. And the dots are the observations. So this model reproduces actually 95% of the absorbers and also other properties. And the accretion rate that we get from this model is again 1 solar mass per year. And the last thing that I like to mention, yes, it's important that this, to some extent, this is complementary to these kinematic models that have been done because these are really measuring the structure and the kinematics, while here there is a dynamical model consistent with another observation that reproduces the data quite well. And the other thing I like to mention is actually with this condensation, with this idea Drummond was describing in his talk, you throw a seed, and then this seed makes lots of hot gas becoming cold, essentially, so condensing. And with this idea, we actually, in this paper here, even managed to reproduce the complex C, the renowned high velocity clouds that is at 10 kpc. If an explosion manages to throw a seed high enough, it is possible to reproduce, to make a portion of the hot gas cooling in the shape of the complex C. So this is what I meant when I said that maybe high velocity clouds and intermediate velocity clouds are not that different. And by the way, this model also reproduces the metallicity if the corona there has enough low metallicity. And the last thing really that I want to say, so this is the last slide, is that obviously all these models have some limitations, but they, in our view, they cannot be overcome by making a simulation of the whole galaxy, because the basis of this idea is that you need resolution of 1 parsec, and you cannot model the whole galaxy at 1 parsec. But people have looked at portions of the disk. And for example, there was this paper last year where they modeled this portion of the disk looking for the condensation, and actually saw the condensation. And so so this is the portion of the disk, a galactic fountain that is developing there. And this condensation can maintain enough the star formation of the Milky Way. And the last thing that I want to mention are these wonderful simulations by Keynote Striker that have been shown already, but in particular, the fact that these simulations predict that at KPC distances from the disk, there is lots of warm gas, which is the gas that we are observing in the extraplanar layer. And last year, there was this very nice paper by Aditi, where she showed that a ballistic model essentially produces the same result that you get through this very complex simulation for the warm gas. So ballistic treatment is in agreement also with this simulation. This is very good news for our models, our old models, because then we can expect that potentially if we could use this type of simulations to model the same thing, we will get similar results. Okay, this brings me to my conclusions. Briefly, what the Milky Way tells us, the CGM has been accreted from at least redshift 1 into the disk, over the disk, at relatively low metallicity, relatively high angular momentum, but not as high as the disk. The cooling of the halo, hot halo, for me is an excellent candidate for accretion. This, we can discuss it as much as you like. The extraplanar gas, so this region, a few kpc above the disk, up to 10 kpc above the disk, has an enormous mixture of disk material and external material, and lots is going on there. This is really the lower CGM. Mark asked me, where does the CGM start? It starts with the extraplanar gas. The extraplanar gas is CGM. And then this is more, my opinion, the fountain-driven condensation can actually explain many of these features and give you an accretion rate of order of 1 solar masses per year. And with this, I stop, and I thank you very much for your attention.
Thank you, Filippo. Everyone clap. We already have hands raised, but we are going to take a convenient break beforehand and start getting to those questions on the hour at 9 a.m. Pacific time. So take a little bit of a break and get a coffee, and then come on back.